countable. Okay, so either A or its its complement are countable. Then by countable I mean what do you mean by countable? So something is countable if it is similar. Okay. So there is a 1-1 correspondence between the set of natural numbers and that set.
Yes, sir.
Okay, so this is what the countability means actually. So and you can also see a similarity between this and something that you've done in topology, for example. So you had something similar. What do you call topological space actually, but in that you didn't have countable thing, but you had a finite actually.
Yes, sir.
And therefore you call it a cofinite space.
Cofinite space.
Okay. Why this guy is going to be a measured space? Let's think about it. So why empty set must be in F? Okay. Because it's a subset of X,
Yes, sir. That's fine.
and it's trivially countable.
Yes, sir.
Okay, since there isn't anything in it, so it's countable actually. So in F, those sets are going to be there, which are countable, or their complements are countable actually. Okay, so this is what the first thing is. How about why X would be in F actually? Okay, why X would be X. Is X countable?
We have two cases.
We have no idea.
Two cases.
Why to have the two cases?
Like whether it's countable.
We don't know. There's no need to refer to the two cases. Think about it. So do we know that X is countable? The answer is no. I don't know. Maybe X is whole real line actually. So but it has this beautiful property that you have X complement is empty set. Empty set is countable.
Yes, sir.
Okay. So therefore X is going to belong to basically this space.
Yes, sir.
Alright. So what would be the second thing? So for the proving second thing, what you need to show that you have to pick an element from your potential sigma field, and you have to show that its complement should also be there. So what you have to do, so you're going to say that let A is in F. Okay. So imagine A is in F, and we want to show that why A complement should also be in F actually. Now if A is in F, it must satisfy this condition. Okay? It must satisfy this condition. So you have two choices now. Either A is countable, I don't know whether A is countable or not, or A complement is countable. Okay, so one of them is true. Okay. Now, if A is countable, then I can write a complement as a complement. Okay. So I would say that since A complement, whole complement is A. Okay. A complement, everything complement is A, and A is countable. So this means that this object whose countable, whose complement is countable, must belongs to F actually.
Yes.
So this must belongs to F. Why? Because this is what the definition is telling us that a set is going to be in F if that set itself or its complement is countable. I know A is countable. Okay. So therefore the complement of A complement must be countable. And if the complement of complement is countable, then A complement must be enough actually. Okay. How about if A complement is countable? If A complement is countable, then A complement is trivially in F actually. You don't need to do anything. Think about it. Just take A to be a complement. Okay? So in both situations, whether A is countable or a complement is countable, in both cases, no matter what happens, A complement belongs to F actually. Okay? So that's what essentially the thing is. What would be okay? What will be the next thing? The next thing is going to be to take basically a countable number of sets from F. And then you have this. Okay? And our claim is to show the union of all these guys also belongs to F. So this is what that we would like to show, and this is kind of given to us. So what will be your version of argument for this? Why this union is countable?
If each of the AI is countable, then the union would trivially be countable.
Good. So you have different possibilities now. Okay. Now, if all of these are countable, okay, then their union is countable. So that's just one case actually. Okay. So that's just case one. That if AI is countable for all I and I, then we know from the analysis that countable union of any number of countable set is countable. Okay? So this guy is countable. And if it is countable, what's going to happen? This must belongs to F. That is, this guy must belongs to F actually. So that's just one case. You will have another extreme case. Okay? No. Not all these are sets are countable, but all their complements are countable. Okay? For all, so AI is countable. AI complement is countable. For all I and I. Okay, so this is going to be the case. Now, from the countability of these guys, how can I deduce the countability of union? And apply the De Morgan's law. So what should I do? So since the union of I, where I goes from 1 to infinity, is equal to what? So union, okay, of I equal to 1 to infinity, its complement and complement, okay, something like this. Alright, what will happen? So you're going to get I equal to 1 to infinity, a I complement, everything complemented.
Yes, sir.
Okay. And now, think about it. If all these are countable, then their intersection is also countable. Okay? Then their intersection is also countable. So I have a set which is countable and its complement is equal to this guy. So what does it mean? This guy must be enough. This guy must be enough. So that's what the definition is.
Because the complement of this guy is inside of this.
Yeah.
That is computable.
Yeah. Okay. So it must be enough. The third case would be interesting.
mixed.
When you have a mixed kind of a thing actually, okay, some are countable and some are not countable. So what should we do?
Take the countables and
One
take
side will take
complement of the uncountables.
Anyway, think about for that yourself actually. Okay, so verify. I'll use this symbol for verifying actually. Okay, verify it for yourself that, you know, in the case when some of the elements, okay, from this are countable and rest are not countable actually. Okay, maybe infinite, maybe finite, whatever.
Sir, by showing these examples, what we will have sigma-algebra or algebra?
Sigma-algebra.
Sigma-algebra.
Sigma.
Yeah.
So we are interested in sigma-algebra. Forget about the algebra. Use algebra. We'll need it actually. ठीक है जी? Is it making sense? Let's move. So we defined what we mean by measure space, sigma algebra. Okay. So the next thing, so in this measure space, the elements. Okay, so in topology, the elements are called open sets.
Yes.
Okay. So in measure space, the elements are called the measurable sets actually. Okay. So it's like in F, whatever the elements are there, so they all are called measurable sets actually. Okay. So elements of.
Sir, I have a confusion, sir. So when we defined measure last time, we defined a mu function from x to the set of positive real numbers or including 0. So here we are just having ordered pair containing x and f. So it will be just sigma algebra field or sigma
Yes, a sigma
structure. So we are calling it measure
Space.
before
Okay,
that.
so it's like, okay, it's a potential set of objects that we are interested in measuring. Okay? But now you have to tell that, okay, with what thing you want to measure it. So what's your measure that you want to measure it? Okay? So when I am using at the moment word measurable space, I'm not, okay, I can say things in a technical space, but obviously this gives rise to a new question that, okay, if this is a measurable set, you know, and maybe it's a collection of measurable set, the question is that, okay, with what measure you can measure them? So this is what that we would like to define next actually. Okay. I would like to highly encourage you to see the first lecture, okay? And in that I have talked about these things in detail. If you think you need, you know, time additionally, okay, and for the first few things actually, if you need an additional time, you may say me and then I can repeat things for you, the same thing that you will see from the lecture, okay? Okay.
After watching the lecture,
After watching the lecture, if you still have trouble, you know, do ask me. Okay. So the next thing that I'm going to define is so-called measure. So consider a map, mu, okay, and it's a map from sigma-algebra, okay, okay, sigma-algebra. So it's a map that swallows a measurable set and give you the measure of that set actually. Okay, so mu is a map from sigma-algebra into the set 0 to plus infinity, where the plus infinity is included in this. We are talking about extended real line. Okay, so 0 to plus infinity, such that. So what does this measure is going to take, do? So it's going to take an element from F, which is a measurable set, okay, and it's going to give you a number, mu of A, which is a measure of this measurable set actually. And obviously we have to define that, what is the meaning of this actually. Okay? Like you do in the functions, okay, you say y equal to f of x, okay, but you have to tell that what is your f. Okay. It's an abstract thing. Such that two conditions are satisfied. That your measure, if it is a real measure, okay, you want to measure something, like it should have this common sensible measure properties actually. That if you have nothing and you want to measure it, what do you think? What size should it give you? 0. So it must give you 0.
Yes, sir.
Any potential measure should give you the measure of empty set as 0. Second thing, okay, that if you take, a bunch of disjoint sets from F, okay, so take disjoint, so all these are mutually exclusive actually, okay, all these are disjoint, then the union, and you want to measure what we call the union of all these disjoint sets, okay, then the union of their measure of their union must be equal to the sum of their individual measures. Okay, something pretty intuitive actually.
Sir, aren't you using the rotation of dot?
Mm-hmm.
Dot the
No, I can
rotation.
put a dot here. Dot is like a disjoint unit. If I have said disjoint here already, so
Yes, sir.
So dot then as a disjoint of that.
ठीक है, this is what that it must be. So now we have a measurable space and we have a measure on it. So what would be, so let's take some examples of a measure. Some examples of measure. Okay. So let's take the first example that I discussed yesterday. I would like to quickly recall that. So take a fix x from the set x, the base set x on which everything is defined, okay, and corresponding to this fixed x, define a map delta. And since this map is corresponding to this x, so I'm putting an x here so that it kind of reminds me that I'm defining a map corresponding to the x. So delta x from f, okay, so what I need to do, I need to specify, let's take x be any non-empty set, and let's take f as the power set of x, actually something pretty simple. Okay. So I'm defining delta x from the sigma-algebra to to 0 to plus infinity, okay, but it's just going to, so I can take 0 to 1, so it's a part of 0 to plus infinity, so it should be okay. Okay, and the definition is going to be that if you give me a set from the sigma-algebra, okay, and if that set, the measurable set, will be swallowed by this map, delta x, then it's going to spit out 1 if x is in A, so it's going to tell me that, I'm inside A, and is going to give you 0 if x is not in A. Okay? and I'm talking about a fixed set. So it gives me two measures, essentially two outputs for each set. That your fixed element is inside that set and or not, basically. So essentially this is what you will like to. And there's an interesting factor, for example, especially about the set theory, that if you take a finite set, for example, and you take a power set of a finite set, then in that power set, half of the sets are going to contain your chosen element, okay, and half are not going to contain your chosen element actually. So there are going to be elements, sets in which you don't have x actually.
So that means corresponding to every element we have a measure.
Yes, I can define a
Or
measure.
yes.
I can define a measure. And then obviously you can generalize it. Instead of taking x, you take set A actually. I can do something like similar. But okay, let's just stick with this at the moment. So I have defined this. So the question is that does it satisfy these conditions? Okay. So when delta x will be operated onto the empty set, okay, and then I have to essentially check if this fixed element is in this set or not actually. So is this element is here?
No.
No. Then the definition tells me that I must assign 0 to it actually. That definition. So this is what the first property is. How about the second property? Okay. That take the disjoint sets delta x of, and these are disjoint, I'm just taking their union, okay, and I want to consider the delta x operated onto the union, and I want to see that whether I'm going to get equal to the sum of delta x of ai's or not actually. So this is what that we like to essentially have. And how we can know that? So I have a set and I have an element. So I have only two choices actually. So either x is going to be in the union, okay, or x is not going to be in the union. Okay? And I'll show that in both cases this inequality holds. So no matter what thing you take is going to be true. Now if x is in this union, this x is going to be inside some ai. Okay? There exists some ai. There exists some ai. Okay? So there exists some ai such that x belongs to ai. Okay? Can this x be in any other ai actually? The answer is no, because you have assumed these all ai's to be disjoint. So if x is in some ai, this x cannot be in some other ai. So there exists a unique actually. So I must say, there exists a unique, I'll use this symbol as well. So whenever I have to say there exists a unique, I'll put a mark of exclamation actually. So there exists a unique ai such that x belongs to ai. Okay? And I would say that x does not belongs to ak. X does not belongs to ak when k is different from this fixed star. Okay? Okay? Now, what would be the delta x of the union I equal to 1 to infinity? Because x is inside this set, so you're going to have 1. Okay? And how about the other side? In other words, if I compute, for example, delta x of a1 and delta x of a2,
Yes.
okay, and plus delta x of, okay, so on and so forth, delta x of ai, in other words, this, and plus delta x of ai plus 1, and so on and so forth. Okay, what this sum is going to be look like. So x is not an a1, so this is 0, okay, equal to 0, plus 0, plus so on and so forth, plus this is going to be 1, and rest is going to be 0. Okay, so what essentially you get is that if you take the sum, okay, sum of the delta x of ai's actually, you will again get a 1 actually. So delta x of union is 1, and sum of delta x of ai is 1 actually. So since both are 1, so we are happy. So it's true in this case when x is in unique ai actually. This case, verify for yourself that if x is not in the union, okay, then so if x is not in the union, the delta of this is going to be 0. And if it is not in the union, it means that it's not in any of these actually. And hence, delta x of each of these is going to be 0. So you have a 0 on one side and the 0s on the other side. So you get a 0. Okay, so almost clear with the proof. But try to write a formal proof for it. Alright? So this measure is called a Dirac measure. Okay? And it has its own importance actually. It's called the Dirac measure. Dirac was a brilliant physicist actually. And a mathematician as well. That's also a contribution in mathematics. Alright. Shall we go for another example? What could be the second example? So let's take mu from, okay.
Probability measure.
Okay, so another thing could be the probability measure. Yes. For that I need to define what's a probability measure. So let me define that. So one particular kind of a measure that we are interested in is probability measure. So I measure mu from a sample space omega into
Sir, before getting in, I was thinking, is area length and these going to be
these are my, this is going to be the key example, so we're going to get into that. So that's what we like to head actually. So this is going to be our key example. Length is a measure, okay, but the trouble is that we can talk about the length of an interval, but what if I say that tell me the length of a Cantor set actually, maybe the length of something which is pretty complicated. So we want to extend this notion of length to the complicated. Yes, we will define it. We will define it. Okay, and we will see some examples for which you can't assign any notion of length actually. They are not measured.
Tarski paradox.
Tarski paradox. Yeah. So I have mu from omega into 0 to plus infinity, where omega is some sample space. Okay. I mean, if I be more rigorous, it would be 0 to 1 actually, essentially, not the 0 to plus infinity. The 0 to 1 is a part of 0 to plus infinity, so we are fine. A measure. So in other words, a measure that has these properties is called probability measure. Probability measure if the measure of the full set is 1.
And what will be our omega?
Huh?
Omega क्या होगा?
Sample space. Sample space. Okay, so it could be any set. strict as any set. So any set, so mu is a map from any set. No, we should say
Sigma-algebra.
sigma-algebra.
Events.
Sigma-algebra. So it's a collection of
Subset.
subsets of 2 to the omega. Okay? So it's a measure, so it's going to take an event and it's going to give you a number between 0 and 1. So events. So a measure, which is a measure, just satisfies these